Hi, everybody. Welcome to another round of Fellows Talks. We have six talks today. The first talk up is Andrii. Andrii, you want to share your screen and get started?
Yeah, yeah, 1 second. I think you can see it right now. Can you see it?
Yeah, we can see it. You can get
Yeah.
started.
So, hi everybody. Uh, yeah, my name is Andrii, and I want to present you my report on a project that we did together with Bridge in our summer project. So it was unifying constraints on long-lived particle feebly interacting particle model, Collider-Cosmology synergy. But in our case, we because the actual topic is a little bit general, we decided to consider a particular problem that exists right now in dark matter community, and I hope to explain this problem to you and also explain how we hope to present our solution to this. So let's start from the beginning. 1 second. So what is exactly dark matter? So dark matter, as some of you may know, is a hypothetical form of matter that was introduced to explain gravitational effects that cannot be explained by only visible matter in the context of general relativity. And it is called dark because we cannot observe it with a visible light or any kind of electromagnetic force. And it generally assumes that it is not interacting with any kind of standard model forces and only interact with gravitationally. And according to current models, the universe contains over 5 times more dark matter than visible matter, so it's actually important to understand what this matter is and where it's coming from. Yes, and in this field, it's actually a very rich field with a lot of scientists working in it. So there exists a bunch of different models that try that kind of they call the candidates to just solve this kind of problem in dark matter. And as you may understand, because there is, as on the left diagram, a lot of models and a lot of people involved, there is no any kind of unified description for most of these models, and because of this, there exist different conventions. People consider different regions or sub-regions in particular models, which can be quite confusing. And as a result, a lot of people who work in the field, they should make some reinterpretation and combine like recent results by themselves with kind of scripts, or I don't know, using different tools because there is no any kind of unified way to do it, and it can be quite frustrating to people. And to go a little bit deeper into this problem, let's go do step a little back. So how exactly we calculate like study constraints in dark matter models? Usually we consider like set of parameters that exist in every kind of dark matter models. So this goes to the set of couplings and to masses of particles that we introduce. Yes, for example, here, this is one of the many models here. So this is scalar Higgs portal model, and here we adding some scalar field that we call chi here, and you can see here this lambda is corresponds to this coupling that we spoke about, and mass is just the mass of this field. So this is basically the two independent parameters in this model, and in different kind of models, the result is this kind of parameter sets. It can be more couplings or more masses, but generally this is like it. And we can build basically the plots from coupling to mass. And this is like where I show this example here for minimal dark photon model. Here you can see that coupling is called actually epsilon, and yeah, mass of this dark photon is showed in electron volts. So what I wanted here to show is the fact that actually you can see that there exists actually subdivision in this like one model. You can see that clearly this is two completely different regions. They do not overlap because one of them starting from 10 to the power of minus 18 up to the 10 to the power of 8 in EV, and another one is just starting from the 10 to the power of 6 and ending in 10 to the power of 12. So, and here is the question, so why is this people doing this, and why we actually think so differently in this for this different plots, and if there is a way to actually unite this in one big plot, and if it's even will be useful. And this is one of the problems that we want to solve in this project. Another one is the fact that it's actually when you have a lot of data in this fast growing field, you may see that this is another kind of model. You don't need to think about it very much, but you can see that in this low mass region, there is a lot of different lines and curves that actually very hard to understand itself. And because of this, authors of this paper even like do this like zoom in to try to explain what is going on in this particular region. And it's also kind of like if you think about it, you make another plot to explain one plot. It's I mean, this is kind of the problems that you have because you work with static plots, and we want also to work with this problem. And again, you need to keep in mind that because dark community again is huge. It's enormous community. You have like 50,000 papers, which is approximately 2% of entire archive database. So it's actually growing community, and there is a lot of ongoing experiments that count dark matter around like 46 right now, and actually some of them are in construction, so it can be much bigger. And obviously you have a lot of research in working on this independently, and the question you will get even more data, and it will be even more harder to make a good plots with this kind of methods. And you can ask how you actually can keep up with all of this when you have this kind of big flow of these papers and updates and so on. How actual person can keep up with all of these updates and to understand what is going on actually in field, and how one can actually in the end use the results of like the most present results. And we also thought about this problem with bridge, and we thought that wouldn't it be nice to have a centralized place where one can look at for the current progress. And we came up with the idea that we think can solve this problem, and we named it Dark Matter Live. So this is a web page that contains constraints in unified manner for generally accepted dark matter models. We consider the main advantages of this approach is that we can create a standardized description for each model, dynamically plot make our plot dynamical, and which make it possible to zoom in particular regions, and like you can do whatever you want. You can go left, right, and it can be useful. And we also hope to update our results consistently, so each model will be up to date every time. And we want we also adding the possibility of adding like different results, for example via GitHub or GitLab. And because we like want to make this as a very like big project with a lot of data going on, you always can take the sources of the data in the code if you want. So it is actually a good place when you can look at if you want the data too. So in our case, we started to implement this model just for one case. This is minimal dark photon model that I spoke earlier. I will not go very deep into it. So basically, we get dark photon that is like a particle, which we refer here as A prime. So yeah, it is comparing to usual photon. It is have a mass. So we have mass parameter, and also in this model we have coupling that we call epsilon that correspond to kinetic mixing with electromagnetic current. So basically, again, we have two parameters which we call mass and epsilon. And in this kind of model, we usually people consider two different regions, one called visible channel, one called another called invisible. So the difference is coming from the fact that if you have the mass of dark photon bigger than the mass of two electrons, you can observe it in the collider, for example, or any kind of like real world. But if your mass is lower than mass of two electrons, it's basically not possible to observe with current detection methods. I mean, we don't consider like neutrinos or something. So in this case, usually people study these models with astrophysical observations and like cosmological measurements and so on. So this is two kind of different regions, and the question is, can we like properly unite them in one like very big plot? And it is actually a little bit subtle question, because if you think about it, there is different papers and different results actually can use different assumptions, and in this case it's actually true that it's possible. Let's start with case where we don't have any assumptions, as I say. So consider the case when you consider dark photon just as a particle, so you don't think about any contribution to dark matter or anything like this. And in this case, it is usually happen in collider experiments and precision measurements. So in this case, you basically obtain model independent results because you don't make any strong assumptions. But there is a case that usually goes to astrophysical observations, cosmological ones, where you make actually assumptions that dark photon is actually a big part, or maybe even the only part of dark matter, and it basically means that there is should be enough dark photons in the universe, which is actually quite a strong assumption. And in a proper way, you cannot actually mix this results together, and you need to be very cautious when you do it. So when we like considered all the steps, of course we need to include our data. We used several sources to it. So we used Axion Limits project as a main source, so it was 50 datasets approximately. Also, we used Fibli Interacting Particles Workshop 2025 for approximately 20 datasets and some other results. And in overall, we get 78 datasets, which is actually quite a lot if you think about it. And right now, I would like to show you the actual web page. So, I mean, we already actually set up it basically today. I don't know if it's go like this. Oh, okay, so yes, so I am showing it right now. So this is a front page for this for our project. I hope it makes some kind of good first expression. So there is some kind of effects, but if you go and look for different models, you can see that there is actually a lot of models that we hope to do, but we can start with only one, like the one that we considered here. So this is minimal dark photon model. And if you go there, what we will see is that there is actually the main part of it is actually this dynamical plot that is here. So actually, I mean, we can move it actually as much as we can here. I didn't make any restriction here, but here it is the big chunk of this 78 different results. So you can zoom in, zoom out. You can, if you want, you can go in any kind of particular regions that might be interesting to you. And one interesting and I think useful feature is that you can hover to this different areas, and you can see the link that will go to the source of it. actually it worked a little bit different on local because there also show the name of the paper but because we set up it only today, it's not working a little bit properly, so we hope to fix it in next day, I guess. Yes, and you can also change like different settings. For example, it will be experiment type. You can change like there will be different experiment type, detection type, time frame. Here, for example, in time frame, you can see actual planned constraints that are usually described as dashed lines. So this is, for example, can be like famous like sheep experiment, another kind of experiment that will be done in future years. You can also use like download the results that will give you kind of a picture that was on the screen at the moment. And also to do this good download pictures, you can also fix the axis as you want to change it like to correctly make a plot as you want, for example. Yeah, so and yeah, there is small description for the model and for the detection methods, and a way explanation how you actually can add your data in the end, on the another page. So this is what we did, and yes, as a conclusion, I would say that we designed and made the foundation for this dark matter life web page, and created as a first example minimal dark photon model implementation. And this is what we did, and yeah, thank you for your attention. Is there any questions here?
Thank you, Andrii. Any questions for Andrii? Nice talk. Thanks again.
Thank you.
Oh, wait, I'm sorry.
No,
Arthur?
yeah, can you hear me fine?
Yeah, we can hear you. I'm sorry, I didn't see your hand up.
Yeah, so this was a nice talk. I just had a question because so when you combine all of these exclusions from different papers, do you did you have some work also to renormalize some areas? Because also a bunch of times the papers they have different exclusion areas depending on parameters like hypothesized branching ratio and others. I mean, it also depends on the different types of models. But do you like renormalize all these limits so that comparing them makes more sense?
Yes, we try to do it. There is, we basically at least try to make them so they will be from the one variables. For example, often some of them working with epsilon squared, some of them working with epsilon, some of them some kind of other like convention they are using. Previously, as I said, there is some of them, especially from cosmology and astrophysical results that are not particularly, I mean, they are model dependent, and you cannot like match them one-to-one with the results, for example, from colliders, because they depend on the correctness of like model, and you need to be very careful when you do it. And we tried to include like every of these renormalization things. I mean, maybe we missed something, but I hope we did it pretty well.
Yeah, so it never
Arthur, just
happened.
if I can add on this, so this is actually, in fact, one of the biggest issues. So whenever, for example, a paper comes in, the turnover time from that paper getting out versus a theoretical or phenomenologist picking it up and then including it in the global picture, that's quite a significant work which goes in there, and it also takes time. This is something which we also, and it's not, I mean, when it comes from phenomenology point of view, renormalizing these limits and putting them in the one single picture, this was like one of the big challenge. And we did had inputs from different people who have been working on that. So that is something which we still need to figure out for all the other models, because they are still like, the physics results are in different forms and shapes, and to put it in a single picture, that's something which is basically a challenge for the whole community as such, and that's what we are trying to solve it here.
Yes, and does it also happen that like you have two different exclusions from different papers, which are harder to compare because I mean they really have different assumptions that you could.
So the one plot that actually includes the idea of this assumption in this one. So because I mean in the red basically it's a kind of experiment that comes from different colliders, and also there is precision experiments that is going on. But I mean the blue ones here is the ones that are coming from cosmology, and they actually very depend. For example, you can choose photon, the dark photon is 100% of dark matter. You can choose photon is dark photon is 1% of dark matter, and the plot will change actually with these different assumptions. So this plots can change in blue one, for example, if you just make a slightly different assumptions. And this is why the most concrete ones here is just the red ones. And if somebody wants like to be very specific and sure that they are correct ones, I guess he should work with this from like red regions, for example.
Okay, thank you.
So moving forward in the sense, I mean, we would be working closely with phenomenologists and dark matter experts in getting their inputs in how, because for now all the work which does they do the manual combination of these limits from different sources and then produce these plots. So one of the things would be to figure out a way to engage them in sort of making it useful for the community so that these global exclusion plots can be done live and integrated. So this would be something which we'll be working closely with.
Oh, yeah,
with
that's
people.
great.
Thanks.
Okay.
Yeah, this is really nice work. Very
Any
nice,
Thank you.
Andrii.
Oh, sorry. Any other questions? All right. Next up is James.
Hey, should I just share my slides or how does it sort of
Yeah,
work?
go ahead and share your screen and your slides. Yeah,
Yeah.
that'd be good.
Great. So thank you everyone for inviting me. And what I will be speaking on today is using a graph neural network for primary vertex finding at LHCb. So as my background, oh, sorry, the slide didn't change. So as an introduction, I will briefly speak about what the primary vertex finding is. So if you have a collision that's happening in a detector, what we see from the collision is the particles that hit the detector, and we need to reconstruct the collision points. The way we sort of do is there are tracks reconstructed from the detector, which are represented in our case by the 9 focal parameters, which are point of closest approach parameters. And from all of these tracks, the algorithm, all of the algorithms sort of has to figure out possible PV position, but it's sort of primary vertex is the collision point, but it's sort of complicated because not all the lines intersect nicely and you don't know which tracks came from which collision. So that's the main challenge of this problem. So what we did is use a graph neural network, which is sometimes referred to as GNN, which is basically a type of artificial intelligent algorithm. What's sort of unique about this approach is the data is not represented as a vector, is represented by a mathematical concept that's called a graph. Graphs in general consist of nodes and edges, and in different implementation, they can have different meanings. So for example, one of the famous example of a graph is social network, where the nodes are represented by the people, as we see in the illustration on the right, and the edges represent friendship or connection between those people. What we did in our model is represent the tracks as the nodes of our graph and the edges as the edges connect tracks that are close to each other in the z dimension. So tracks that hit the detector close to each other are connected by an edge, but edges by themselves don't have a physical meaning behind them. why we sort of connected close nodes with edges is because the mainstay of graph neural networks, which is called message passing. Basically, what happens in message passing is the model takes the information from the neighboring nodes, which would be the people in the orange here, and all of that information influences the track node prediction, which is this green person over here. And that's something which sort of allows models more flexibility to use the information from other data points, not just one data point by itself. I'm going to go over the background of how the algorithm works so people can hopefully follow what I'm speaking about. So the way it works is we have an event which can be seen in this plot on the right. So this is just the event in Z and uncertainty in Z. So you can see all of the points here are actual track positions and their uncertainty, and the vertical lines are PV positions, like from the truth information, because this is a simulated event. So we can see all the tracks are sort of clustered around the PV positions, but it's not necessarily, but if you just had seen it without the vertical lines, it would not necessarily be obvious where the positions are. So the way our algorithms work is we take these tracks, they're the nodes of our graph, we connect close tracks, which are the edges of our track, and again, this is done based on the distance. So this is the first step, we need to construct the graphs. Our next step is actually using the graph neural network to predict the PV position for the graphs. So basically, the neural network predicts node-based position. So each track is assigned a position of a primary vertex where it likely came from, and this plot usually looks like the histogram on the right. So since this is per track data, we need to produce a final list of PV positions per the graph. So this is done by a clustering algorithm, which sort of takes all of this track data over here and groups the track in these groups on the right. So each color is one group. And all of these separate groups are groups of tracks that likely share the same PV. And what we do is we assign a predicted PV value for each group. So the prediction is not per graph. You can have multiple predicted PVs per graph. So it's sort of dynamically generated depending on what the GNN determines the likely positions are. So this is a bit of a background, and I will just briefly go over how the model works. It's a bit complicated, but my main idea behind it is, as you can see, the model consists of multiple multi-layer perceptron layers, which sort of feed to each other, and then produce the final output, which is a node track parameter. And this step here is called message passing step, which is repeated multiple times, and it sort of feeds the output of the network back to itself to sort of refine the information we are producing. So I will now go over what I worked on in this model, which is optimizing the initial model developed by Simon Akar. So everything what I showed you in theory is something I started with, and what I was looking into was trying to optimize the model parameters both in terms of efficiency and false positive rate and computational requirements such as processing time or memory usage. So I looked at all of the 3 steps I showed in the previous slides, but for the sake of time, I will just summarize some of the most interesting findings we sort of had. So basically, one of the first things I tried to optimize was the training time, since we want to make sure the models converge faster so we can see results fast. So by changing the batch size and the learning rate along with turning on the smaller data set, we were able to conduct shorter tests and also get the model to converge faster. So this plot here is the loss plot, and as you can see, the optimized parameter result in convergence much faster than the original ones. So that sort of helped us both train the model faster and perform the subsequent tests. So one of the interesting results is we were actually able to decrease the initial model size from 256 neurons to just 64 neurons. And as you can see on this plot on the right, the memory usage the model occupies decrease dramatically this way without just much difference in the performance. But if you sort of go below the threshold of 64 neurons per hidden layer, the decrease in efficiency is going to be much more prominent. So that's why we sort of start with 64 hidden neurons per layer. The next interesting result was the clustering algorithm, which actually allowed us to increase the efficiency in a really good way. So as I mentioned, what the clustering algorithm does is takes the GNN per track predictions and gives us the final list of the PVs. So it's a very important part of this whole process. And what we sort of did is look at the 10 manually coded initial steps and look at what each step does and sort of merge some steps that were not combined in an optimal way and decrease the overall number of steps. So it's actually also faster. And as you can see from the green star over here to the cyan star over there, it has much better performance. So I also want to touch upon some limitation of this approach. The efficiency tends to decrease slightly for PVs that are close to each other in the z-axis. And this especially happens when one PV, like this sometimes happens because like one PV has more tracks than the other one. So like the PV with 0 to 24 tracks sort of gets absorbed to the one that has like 50 tracks. So that's one of the limitations of this model. And also the efficiency sort of drops if the PVs have less tracks. So the model is great at determining PVs with a large number of tracks, but the slightly worse at PVs that have smaller amount of tracks, as you can see here. And the last thing I sort of look at was alternative way to sort of use GNN for PV finding, which is utilizing edge prediction. So as I mentioned previously, the models have node and edge-based values, and previously we were sort of just using the edges to help us better predict the PV position per track, which are our nodes. What I sort of implemented is trying to predict which tracks are from the same PV. So each edge is assigned a number by the graph neural network, which represents the value between 0 and 1. And based on this value, we can say these two tracks came from the same PV or these two tracks did not come from the same PV. And sort of how we get a list from this sort of algorithm is we take the graph, we disconnect edges that are below a certain threshold. So it's unlikely the tracks came from the same PV. And then we have sort of isolated groups of graphs which are disconnected, and each of the graphs sort of should represent a separate PV group. So we just take an average position of those tracks, and that gives us a list of predictions for that event. And this sort of ended up having a similar performance to the node-based GNN, even though it's a different model. So you can see the red star is somewhere between the green and cyan star, but again, this is something that it's really new, so there could be some improvement in the future. And in conclusion, I would just like to summarize is what we sort of looking at is improving the initial parameters of the GNN, which was the basically both the computational and the performance parameters. We were definitely able to decrease the memory usage by switching 64 hidden neurons per layer instead of 256. And what I sort of want to conclude the talk on is, even though these are just some of our first results, it's really interesting on how like different types of graph neural network and machine intelligence can be implemented for PV finding in general. So again, I would like to thank for your attention and thank all of my mentors for supporting me through the project. And I think that's all from me, and I think we can go to questions.
Thank you, James. Nice talk.
Yeah.
Any questions for James? All right. No questions. All right.
Yeah.
Thanks again.
Yeah. Thank you as well.
Yep. Next up is Yehyun.
Hello, hello.
Hello.
Hello. I'm gonna share my slides real quick.
Okay.
Okay, hopefully everyone can see that.
Yep.
Okay. Well, okay, so this is going to be kind of a recap of what my project was over my fellowship at IRIS-HEP. So title would be splitting Uproot into two phases, metadata reading and data reading. So to give an introduction on the context, so we're going to have a CMS phase 2 upgrade, and that's going to output a lot of data, I think over 10 times the data that we have now. And Uproot, which is a Python library for reading root data, is widely used. And to support the upgrade, Uproot has to be more robust and extensible. So there is kind of a lot of work to be done there. And okay, so let's get into what root is. I'm pretty sure that a lot of people know what root is and what root does, but it is like the data backbone of most things in high energy physics. So it's not like having data in CSV or JSON, but it is a custom binary format which is optimized for performance. So at the lowest level, root uses streamer elements to describe how data is stored. So like how the names, types, sizes are stored in the binary file. So yeah, there's that. And the structure is also hierarchical. So you have a T file which contains metadata and streamer info, and inside that there are T directories which hold objects or subdirectories. And each object, which is like the actual data, they are referenced by a key, which also provides metadata. So there is like a literal tree of metadata and data in a root file. So that is something that Uproot works on. And lastly, one important feature is that the class definitions are actually not fixed. So root can rebuild class definitions from streamer info. So this is a powerful feature, but it also makes decoding pretty tricky. So Uproot aims to do that in pure Python. I think I mentioned that, but wait, hold on. So the idea behind root file spec is separation of concerns. So on the right, I have a neat diagram. Up there is Uproot, which handles the low-level decoding and high-level Python interfaces. But now we want to split the concerns into awkward arrays, which handles data and it like represents the data, I think. And fspec actually reads the data. It lets you open files and with the interface. And root file spec is the new piece that only focuses on buffers from Python objects. So yeah, takeaway is that we want to separate the concerns and have knowledge continuity from Uproot, and we also want to have stronger typing, which is an added bonus. Okay. So let's look at the base class here. So in root file spec, each root object is represented by a Python data class shown here. So like let's say a T file or a T directory, they are data classes. And these all have two main methods. So first is the read method, which decodes fields from a binary buffer, and update members, which fills in a dictionary of members. So what we're trying to do here is that we isolate this responsibility for each object, and this makes the decoding process pretty modular because every object knows how to read itself, and each object can expose its fields in a standard way. So that's kind of the technical background. So let's look at an example process. So, okay, so let's say we have a binary root file. So you start with a raw byte, and these are wrapped in a data buffer, which is immutable and keeps track of your position as you like read through the binary file. And after let's say the buffer has methods like unpack, which like if you know Python, .unpack just uses the struct module to decode values, and that also returns a slice of bytes. And when you call tfile.read, it uses a buffer to pull out the header fields. And when these are read, rootFileSpec builds the data class. So the pipeline goes from raw bytes to buffer to decoded fields and structured data Python object. And since we are integrating this new package rootFileSpec with Uproot, we want to take a look at how Uproot decodes binary data as well. So they have a similar but separate pipeline. So when you call open, it creates a read-only file and returns the root directory, and that in turn builds key objects from the file cursors, and each key has a class name, so like ttree. And lastly, they call a class _named, which builds a deserializer class. So how this is different from rootFileSpec is that they have different objects for deserializing and the Python object. So it kind of abstracts all the complexity by wrapping it in a Python interface, but the deserializing part is actually different. So how I bridged this process with rootFileSpec is that I added a adapter object to just replace the whole metadata reading part. So since rootFileSpec already can do deserializing by itself, I just made a wrapper class. So these kind of translate the methods and properties, and the class createAdapter class actually makes the adapter subclass, and these have the behavior from rootFileSpec, but it also has the specifications according to Uproot, so that it is able to be used with the rest of Uproot's API. Okay, so I think I covered this. So root serializable, Uproot model adapter, and createAdapter class. Okay, so I think I'm running out of time, but to get into the design like a little bit, rootFileSpec provides a modular decoding layer. Uproot stays focused on the high-level API and analysis logic, and the adapter just ties them together, making sure that Uproot's public interface remains intact. So this will make the code base easier to maintain and extend. And like for example, if we added support for a new root type, we could just do that in root file spec instead of digging through the whole database in Uproot and affecting their higher level logic. All right. Lastly, for future directions, so the project is pretty much done for basic objects. So there are some deeper integration projects that I would be working on. So first is some more complex root objects. So like STL containers, which are kind of like vectors of doubles and integers and version T trees. So we had to work on versioned objects, and I think T trees is one of them that still needs to be worked on. There are some performance optimizations to be made, and what my advisor suggested is that we could look into wrapping some parts with Rust so that the performance could be improved. And lastly, we would like to implement some logic for incomplete or broken streamer info. All right, so together these improvements will make sure that Uproot and root file spec are ready for the future experiments. All right, and I think that is about it. Thank you for coming to my talk. Yes, Alex.
Thanks. Yeah, this is a cool project. It's quite nice to see this refactoring to kind of separate the areas of concern. You talked a bit about sort of a potential Rust rewrite already. I was curious whether you've looked at the performance from just using root file spec as is at the moment. Does that significantly impact performance? I'm not sure if that's something you looked at in the context of your project.
So yes, we've run a test on that, and I'm pretty sure that the actual deserializing part doesn't take as much time, but I think loading in the objects and compiling the different files takes up the majority. So we'll see where that goes from here. But I think performance-wise, I think it's like about the same like time complexity.
Okay, cool. Thanks.
Okay. Gordon?
Yeah, really nice talk. And as Alex said, this is some very nice work to see. Pardon me. I was just wondering, and maybe you mentioned this, but I missed it. As RN tuple shows up, is how does this work fit in with that?
So RN tuple, I think Samantha was working on that over the summer, and I think that is coming along quite nicely. And yeah, I'm not the one working on that, but I think we have RN tuple support now.
Yeah,
So you
no
can
worries,
check
no
on
worries.
that. Yeah.
Yeah, thanks. I know I know other people to ask, so I can ask them.
Yeah, but yeah, my primary concern was just bridging with Uproot, and not root file spec itself, mostly.
Right.
Right.
All right. Thank you, Yehyun. Any other questions? Excuse me. All right. Next up is Andrii Len.
Yeah, hello.
Yep, you're up next. Go ahead and share your screen.
Can you see it?
Yes.
Okay. Hi, everyone. My name is Andrii, and today I want to present with Dmitro Kowalski project, which is called Mitigating the Impact of Simulation Mismodeling on DNN Training, Building Robust DNNs in the Presence of Detector Mismodeling. First of all, the main target of this study is key-short to mu rare decay with an expected branching fraction of the order of 10 to the negative 12th power. During this study, we were using 3 years from run-3 CMS data. And as our decay is very rare, our main objective for this study will be to significantly reject combinatorial background. You can see the example of the spectrum we will be working with on this plot. So in order to reject combinatorial background, we will try to improve our machine learning approaches. We first of all gathered data and features, 36 features for training in total. They are both primary detector response and some high-level features also. They can be divided in 5 groups: diamond vertex quality, flight length, diamond vertex isolation, production mechanism, and kinematics. Then we started with training a simple model which uses key-short to mu simulated signal against key-short to mu combinatorial background from real data sidebands. But after we trained this model, we started questioning ourselves to which extent our models are indeed training to separate signal and background rather than separating simulated and real data. In order to answer this question, which is actually a pretty common problem in the recent studies, we know a lot of people who face them also. So in order to answer the question of this potential mismodeling, we applied our Monte Carlo versus data model to key-short to pi Monte Carlo and data samples. We will further call these key-short to pi samples control samples. And we checked on these samples for mismodeling, and it showed up to be concerning. And as we established that we indeed have some mismodeling, which our models are learning, we needed to introduce corrections for this mismodeling. And as you can see in the last column of this table, corrections are pretty huge, especially at tight selections in which we are particularly interested, because we need a strong combinatorial background suppression. So in order to try and get lesser mismodeling, we decided to try other approaches. First, which we tried, we called it real data versus real data approach. As you can see on this illustrative picture of our spectrum, we are lucky to have a huge signal-like background from key-short to pi to Mons to neutrinos, which we can use as a signal to train our models. And the combinatorial background we will still take from data sidebands. This approach showed pretty impressive results, but it had its own uncertainties, so we decided to try and adjust and improve our previous Monte Carlo versus data approach to see what we can get. So we studied a lot of literature and papers of other common studies which also face problems of mismodeling, and we took inspiration from them. Inspiration predominantly because these studies are usually connected to jets physics and are hardly and not directly applied to our key-short to mu study. That is why we took inspiration and proceeded to develop our own approaches. And what we developed can be divided into 2 tasks, 2 tasks of training. The primary task is binary classification of key-short to mu signal from Monte Carlo samples and key-short to mu combinatorial background from real data sidebands. And the secondary task is trying to mitigate mismodeling, which our machine learning models will try to learn using key-short to pi Monte Carlo and real data as control samples. For secondary task, we developed two strategies. First one is visualized here, is training a separate reversed machine learning model called Extractor on K-short to PyPy samples, which will produce a representation of the feature vector hardly classified as either simulated or real data. And then we can use this extractor to train K-short to Mu classification model. And the second strategy is training on K-short to Mu and K-short to PyPy samples at the same time, but adjusting loss function to constantly cross-check with K-short to PyPy on how much the model sees the difference between real data and Monte Carlo. Before moving to the results, there are a few properties of our machine learning trainings which are similar in every strategy and approach we took. Here they are listed. For example, we are using TensorFlow Keras, standard scalar, not very massive DNN architecture, means 3 to 4 inner layers with neurons in range from 256 decreasing to 16. We actively used batch normalization, and for Monte Carlo versus data approach, we also use dropout and sometimes regularization. And other characteristics similar for both approaches are listed here. Regarding K-short to Mu samples, we have about 1 million simulated events available for training and 10 million events of combinatorial background data also available for training. Regarding K-short to PyPy control samples, we have approximately 50,000 simulated events and 400,000 of real data events. Also, in all our trainings, we used a K-folding strategy. Now to the results and comparison. First of all, let's compare the two strategies of Monte Carlo versus data training. And let's compare them based on the mismodeling. As you can see on this plot, mismodeling corrections required for both strategies of Monte Carlo versus data training are pretty similar, but second strategy is like 10% better overall. And the same performance we can see on the ROC curves, which represents a raw classification power of the models. We can see that second strategy is also better. Second strategy, I'll remind, is the one where we are adjusting loss function. And so we took the best Monte Carlo versus data strategy and compared it to our data versus data strategy. And as you can see, data versus data is better by both mismodeling corrections and by classification power. But in defense of Monte Carlo versus data approach, our new Monte Carlo versus data approach, it is significantly better than what was before. As you can see, this curve represents old Monte Carlo versus data approach, and our new corrections are approximately 2 times better, which is pretty impressive. So as a summary for this fellowship, during this fellowship, we studied multiple similar cases from known analysis, which also face the problem of mismodeling, and took inspiration from them to develop our own data versus data and Monte Carlo versus data DNN approaches to separate K-short to Mu signal and background while using K-short to PyPy control samples to mitigate mismodeling. We compared two strategies of Monte Carlo and of Monte Carlo versus data training. Both of them showed a huge improvement in comparison with old approaches. But the second strategy with an adjusted loss function worked better than training of a separate extractor. And finally, we compared data versus data and Monte Carlo versus data approaches and concluded that data versus data is in its current state is better. As you can see from this table, data versus data model is able to suppress combinatorial background almost to 0 level while keeping approximately 10 to 15% of signal, while corresponding Monte Carlo versus data metrics is 2 times lower. And by mismodeling corrections, data versus data is also more powerful. In conclusion, this study significantly increased sensitivity of the CMS experiment to rare diamond final states and is about to give valuable insights in the mismodeling problems. Thank you for your attention.
Thank you, Andrii. Any questions for Andrii? No questions. All right, thanks again. Up next is Cody.
All right, let me share my screen.
Okay, great.
All right, everyone see it?
Yes.
All right. Hi, I'm Cody Tanner. I'm at the University of Washington, and my project this summer was differentiable modeling of systematic uncertainties in Atlas object corrections. So here's a quick look at the analysis pipeline. So we start with matrix element calculation, and this pipeline shown is just for the simulation aspect. There's a whole nother pipeline for actual detector results. But we start with matrix element calculation, where we determine what processes we want to simulate. And then we have parton showers, where we have those particles from the collision split out and go into our detector simulation, where we simulate how much material would be deposited in each layer of the detector and how the detector actually would see the collisions. And then we move on to digitization, which is where we take those raw signals and we move them into the actual data. And then we have, in this arrow before the analysis, is what's called the jet energy scale corrections. And so from the simulations, there's a correction applied to the data to make it match better the actual detector data. And so this little bit right here is what this project was all about. So the challenges for the current corrections are that corrections are applied over a series of multiple stages, and they're a function of many different variables. They're slow to evaluate at scale, they're computationally expensive, and they're non-differentiable, so they won't work in any gradient-based workflows. We can solve these by replacing the current algorithm with a neural network. Now, neural networks are fast, even at large scale, computationally inexpensive, and differentiable. They essentially boil down to matrix multiplication. So we need to learn a function f of x, where x is all the dependencies of the correction algorithm. So the pt, the eta, the energy, and many different event level variables as well. So for this project, we are going to be trying to predict the momentum in the x, y, and z directions. So we'll look at the data in the pre-processing first. So we had the matching stage, which was event local. So we looked inside of an event from the uncorrected data and an event from the corrected data. And we minimized the delta r squared between them. So we minimized the angular separation. So basically, if two jets are pointing in basically the same direction, then we can say that that uncorrected jet became that corrected jet. And so that's what we trained our network on, was many different kinematic variables. We had the PT, eta, phi, energy, px, py, pz, the width, and multiple event level variables like the number of primary vertices, the average number of interactions per crossing. And so, you might look at this and say, oh, you have PT, eta, phi, you don't need px, py, pz. And well, yes, I agree with you. The neural network performed better when you gave it all of these parameters. So we may as well give it all it can. And then we had a standard normalization strategy for neural networks. So our target, well, we started with the direct px, py, pz regression. So predicting straight into px, py, pz. But that gave a very high variance in our data. And then we moved into ratio space. So predicting the px corrected over px uncorrected. So basically predicting a correction factor. And this improved stability significantly, cutting the variance down approximately in half. And then we moved into log space, where we take the log of this ratio. And this improved the variance even more, again, cutting it in half down to what we have now. So we'll look at the model architecture. So we had a 6 fully connected layers with batch norm and dropout. And there's one layer of gated eta being less than 2.5 or greater than 2.5 with dual heads. And we'll get into the motivation of this more later, but it's important to note that eta being less than 2.5 dictates whether or not you're in the end cap or the barrel of the Atlas detector. So we observed very distinct behavior, and I'll show graphs later on to show that. And we did try late fusion of eta, so giving the network eta again near one of the end layers. We tested it, didn't improve performance at all, but the dual heads did, so we kept that. But this does motivate future exploration of more study around why this eta changes so much. So the loss and training, pretty standard. We used the mean squared error in normalized log space that we were predicting in, atom optimizer, and reducing the learning rate for around 100 epochs. So here's a look of what the model architecture looked like. It's not to scale, but we have our 6 fully connected layers in the middle here. And then we have 2 heads right here, one for eta less than 2.5, one for eta greater than 2.5. And then we combine them here using what's called a softmax gate into our final PX, PY, and PC on the side. And so the softmax gate is there so that the neural network stays differentiable. It effectively says, it combines these two using a linear combination. And basically, the closer to 2.5 you are, the more you're going to get a little bit of both. But if you're farther away, then you'll really just get one. So now let's look at how the model actually did. So first we needed to reconstruct. So we undid the normalization, exponentiated it to get out of log space, and then multiply by the PX, PY, PZ to get that ratio factor. So a couple of the metrics we had was the mean percent difference and the standard deviation of the percent difference. And we can have the same for the mean absolute error. And then we can also look at how the model did in region specifics. So again, that eta cutoff. So the results progression, we started out with very high variance. So the neural network always learned to be very accurate with the mean, because the mean squared error will always optimize the mean of it. But the variance was quite high. And so when we're looking at percent differences here, what we're looking at is the percent difference between the prediction of our PX, PY, PZ and the true corrected PX, PY, PZ. So we started out where we were computing it directly, and it was about a 10% standard deviation of error. But once we moved into ratio and log space, we got that down to around 2.3% standard deviation error, which is just shy of a giga electron volt. So here's our a graph showing the PX percent error histogram. I chose to show only PX here. PX, PY, PZ all basically looked the same. So for the interest of time and space, we may as well use just one. Where you can see the mean is very tightly grouped at 0 with very small standard deviations on either side. And we can see in this plot here, this is a heat map in log scale. As the true PX grows, so does the absolute error. And that makes sense. The more energy something has, the harder it is to measure it exactly right. And so here's what we were talking about with the eta versus absolute error. So eta is on the x-axis and the absolute error is on the y-axis. We can see here clear cutoffs between 2.5, eta being less than 2.5 or greater than 2.5. And we also have that the absolute error standard deviation of PX being less than 2.5, so inside the barrel, is around 1 giga electron volt, while outside of that region, it's only about 0.28 giga electron volts. So there's a very clear difference here, and this motivates future study into, why is it so different inside versus outside, and how do we fix this in the neural network while keeping it differentiable. So, we need to explore how to improve that region, incorporate uncertainty modeling into this project. That was one of the goals from the start, but we did not have enough time in the summer. So hopefully later on in the year, we'll be able to do that. And then I'd also like to build a Z to jet peak and compare it to the current corrections. This will give some physical context into the error, how much of this error is actually how much is the error actually affecting the data versus just being residual error because neural networks aren't perfect. So is there any questions? Yeah, Alex.
Thanks. Yeah, this is a very interesting project. I'm wondering if you've run into any issues where essentially, like you have in the beginning this kind of matching that you do between jets, so that you like figure out what to learn. But then there are scenarios where a jet is no longer a jet because it has changed in a way that makes it no longer qualify as a jet. I don't know if you ran into this in this project in any fashion. Like one example is if I define the jet to have a certain PT requirement, for example, and then after some variation it drops below that, now suddenly it's gone. And then there's no way anymore in some sense to like map continuously from one jet to another. Have you encountered this in any way or like in this project?
A little bit. So when we look at the data, there's way more uncorrected jets than there are corrected jets. And so what we did when we matched is we'd loop through the corrected jets so that every corrected jet we know has to have come from an uncorrected jet, but not every uncorrected jet has a matching one. I'm not sure if that answers your question or not, but
that's interesting. Do you have an idea why those numbers are so different between corrected and uncorrected?
Yeah, so I think it's not all I'm not exactly sure like the full reason. But I think not all jets get corrected, or maybe it wasn't included in the data set. I'm not fully sure why. Yeah. Yeah, Gordon.
Yeah, I just wanted to say, Cody, you despite my absence and travel schedule, you made a huge amount of progress. You kept saying we did this, we did that in your talk, but I just want to make it clear to everybody that it was you that did all of the work with very minor guidance from myself. But really, very, very nicely done. Congratulations on the work.
Cool. Thank you. Any other questions?
Any other questions for Cody? No. All right. Thank you, Cody. Up next is, sorry, I lost my to Eglė, sorry.
Yes, hello. Can you see my slides?
Yes, we can.
Okay, so my project this summer was adapting the Coffea framework for FCC. So my name is Eglė, and I study in Vilnius University, and my mentors for this project were David Lange and Priya Gedda. So the Future Circular Collider is a planned particle accelerator. It will have a potential to reach 100 tera-electron-volt collision energies. With increased data rates and more precision, we will need a more robust data analysis framework to fully exploit its scientific potential. So the columnar object framework for effective analysis, or Coffea, is a Python-based unified analysis toolkit for high-energy physics data. Coffea provides tools and components that simplify data analysis, enabling streamlined and reproducible high-energy physics workflows. So the goal of my project was to create a documented example of using the Coffea analysis framework with FCC electron-positron mode simulated data. And so to do that, I created documentation for the data analysis code and combined it into a single Jupyter notebook, and the analysis is of 4 leptons. Adapted the code to the latest Coffea version, executed the code on a DAS cluster instead of running locally, And I also updated the storage of results in histogram plotting, switched to a category-based histogram for comparing multiple data sets. So this essentially draws 2D histograms and saves the process names. And here's a link to my notebook to what I did. So for leptons analysis is an analysis of simulated high energy collision data targeting for lepton final states at the FCC electron-positron mode, focusing on Higgs boson decays into two Z bosons, out of which one is on shell and one is off shell, which subsequently decay into 4 leptons. That is most often for muons. And 4-lepton final state is often referred to as the golden channel due to its low background contamination and excellent reconstruction potential in detectors. From a physics standpoint, this process allows precision measurements of the Higgs properties such as mass, momentums, and etc., and serves as a probe for possible deviations from the standard model. However, the signal competes with several irreducible and reducible background processes, which can be production of Z pairs, W pairs, ZQQ, and other Higgs decay channels like going to bottom or term quarks, taus, gluons, etc. that may mimic the 4-lepton final state. So the workflow begins with the definition of datasets corresponding to both signal and background samples, including their cross-sections and integrated luminosities. A set of physics observables is then reconstructed, such as invariant masses of lepton pairs, 4-lepton invariant mass, visible energy, missing momentum, and isolation variables. These are analyzed across successive selection stages, also called cut flows, and designed to enhance the signal to background ratio. The analysis produces histograms and summary tables of event yields for each process, comparing simulated predictions under realistic detector assumptions. So I also included some of the code excerpts from what I did. This is the running on this cluster, the code, and so it creates an instance of my analysis processor, which is for leptons. Then it connects to a desk cluster, creates a Coffea desk executor, and initializes a Coffea runner, which then loops over datasets in file set and saves the results. So to conclude, the script is running a distributed Coffea analysis with Dask. It sends chunks of event data to a Dask cluster, processes them with my custom 4-leptons analysis logic, and then collects the results and saves them. This here is my output structure. So first defines the selection stages and applies selections and builds physics variables. Then builds the Coffea output and returns the structure's results. So this is in my 4-leptons processor, and this code is building a cut flow based analysis pipeline for each selection stage, like cut 1, cut 2, and etc. It applies the cuts to the event data, computes relevant physics variables, fills histograms, and records cut flow information. The results are then stored in Coffea accumulators, which can be merged across distributed workers. And the last excerpt that I put in is my histogram structure, which I said now, well, I changed it from 1D to 2D, so it saves the process names. So it extracts histogram properties and then defines the histogram object, which effectively builds it to the histogram structure. On x-axis, we have a physics variable, and on categorical axis, we have a dataset name. Then it fills the histogram, and later we have samples that can be kept separate but later merged. And I also put in some graphs from my analysis code. So we can see here fermions mass, Z resonance mass, Z non-resonance mass, which the on-shell and off-shell, we can see a peak at Z boson mass, which is 91 approximately. The on-shell is a narrower peak around Z boson mass, and off-shell is a broader and mostly distributed at lower energies. Yeah, and the fermions mass, we can see the peak at the Higgs boson mass. And here we can see the missing momentum, minimum momentum among the four lepton, the fermions, and visible energy excluding the muons. So again, just distributions of this process. And also reference to an article that I read and based this on. So that's it. Thank you. Do you have any
Okay.
questions?
Any questions? Okay, no questions. Thank you for the talk. That's all we have for today, everyone. Thank you all for attending. Thanks to all the fellows and their mentors for their nice work this summer. More soon.
Thanks, everybody. Bye.
Bye.